You see them every day, right? On street corners, in substations. Those gray boxes just kinda humming along. We barely give them a second thought. Well, today, we're gonna change that. We're pulling back the curtain on the true unsung hero of our electrical grid, the transformer.
All right, so let's just jump right in with the question that sounds simple, but is actually super important. A power plant makes a ton of electricity, right? So, why can't we just run a really long extension cord from the plant straight to your house? The answer to that is the entire reason transformers even exist.
So, here's our game plan for today. We'll start with the big, high-voltage problem. Then, we'll look at the incredibly elegant magnetic solution. We'll explore the whole world of transformers, and trust me, there are a lot of them. We'll also see what happens when these good transformers go bad. And finally, how do we give them a health check? It's gonna be good.
Okay, first up, the high voltage problem. To really get why the transformer is such a genius piece of tech, you first have to understand why electricity can't just travel as is. It basically needs to wear disguise for its long trip across the country.
The number one issue really comes down to one word: waste. When you try to push electricity through hundreds of miles of wire, a whole chunk of that precious energy just disappears. It never makes it to your home. It literally just bleeds off into the air as heat.
And the physics behind this is pretty wild. It's called copper loss, or if you want to get technical, I squared R loss. Now that little formula tells you everything. The power you lose is tied to the square of the current. So think about that for a second. If you double the current, you don't just double the energy loss, you quadruple it. So the absolute key to moving power efficiently is to get that current as low as you possibly can.
And this slide right here perfectly lays out the big dilemma. See, to get the current super low for that long-distance travel, you have to crank the voltage way up. We're talking hundreds of thousands of volts. But you obviously can't have that kind of voltage coming into your house to power your toaster. That would be bad. Very bad. So we need a way to have both, right? We need super high voltage for the highway and nice, safe, low voltage for your home. So how do we solve this puzzle? Well, that brings us to section 2, a simple magnetic solution. This is where the transformer makes its grand entrance. And what's so incredible about it is that it solves this huge problem with, get this, 0 moving parts. It's just pure, beautiful physics doing its thing. It all comes down to a principle called electromagnetic induction. Basically, when you run an alternating current through a coil of wire, it creates this pulsing, changing magnetic field all around it. Now, if you place a second coil of wire inside that field, the field itself will magically create a voltage in that second coil. It's wild. It's like transferring energy through thin air, without the wires ever touching.
And check this out, the secret to changing the voltage is just the number of times you wrap the wire in each coil. That's it. At the power plant, a step-up transformer has way more turns on the output coil, which boosts the voltage up for its long trip. Then, on the pole outside your house, a step-down transformer has fewer turns on the output, bringing the voltage way down to a safe, usable level. So simple, but so clever.
And they do this job with an efficiency that is almost unbelievable. A big power transformer can be over 98% efficient. That means almost all the energy that goes in comes right back out, just in a different form. It is about as close to a perfect energy conversion as you can get.
And that brings us to our third section, a world of transformers. Because, those gray cans on utility poles, they're just the tip of the iceberg. They come in an absolutely mind-boggling range of sizes for some very specific and very important jobs.
You have the absolute behemoths, the power transformers at generating stations. Then there are the familiar distribution transformers in our neighborhoods, but they also get tiny. That little power brick that charges your phone, yep, there's a tiny transformer in there. And then there are instrument transformers, which are pretty cool. Their job isn't to move power, but to safely shrink the voltage or current down so we can measure what's happening on the grid.
But of all the different kinds out there, some have a truly critical job. They're designed not just for efficiency or for measurement, but for the direct protection of human life.
These are medical-grade isolation transformers. In places like an operating room, even the tiniest stray current from the grid could be fatal to a patient. So what these transformers do is create a complete electrical bubble. It's called galvanic isolation between the grid and the medical device. This makes absolutely sure that no stray current can ever reach the patient. They are, quite literally, lifesavers. So, transformers are efficient, they're versatile, and they even save lives. But they aren't invincible. And that leads us to our next section, when good transformers go bad.
The threats they face really fall into two main camps. You've got your external faults. These are the big, dramatic events like a lightning strike or a massive power surge. But the more sneaky threats are the internal faults. These are the slow burn problems, insulation breaking down over years, the oil inside getting contaminated, or the most common culprit, simply overheating.
And this chart shows just how important cooling is. The bar on the left, ONAN, is the transformer's power rating with just natural air cooling. It's rated for 20 megavolt amps. Now look what happens when you just add fans for forced air cooling, ONAF. Boom! Its capacity jumps to 25 MVA. This means if those fans fail, the transformer's capacity instantly drops by 20%, and if it's already heavily loaded, it's going to start to overheat, and fast. Which brings us to our final section. Since a failure can be so catastrophic, how do we know if a transformer is getting sick? Well, it turns out we can give it something that's a lot like a blood test.
I love this quote from one of the sources because it makes the idea so clear. The insulating oil inside a transformer is like its bloodstream. It circulates everywhere, and just like our blood, it picks up chemical clues about the health of the entire system.
The technique is called dissolved gas analysis, or DGA. The idea is that different kinds of stress, like a slow overheat versus a high-energy electrical spark, break down the oil and insulation in different ways. And each type of breakdown creates unique key gases that then dissolve into that oil.
So, by analyzing a sample of that oil, engineers can read these signals like a detective. As this table shows, finding a lot of carbon monoxide points to the paper insulation getting too hot. But finding acetylene? Whoa. That's a major red flag for arcing, a really serious electrical fault that could lead to a big failure. Each gas tells a different part of the story.
And the process itself is pretty straightforward. You take a sample of the oil, run it through analysis in a lab, identify which key gases are most prominent, and that tells you exactly what kind of trouble is brewing inside the transformer. This lets crews make repairs before a catastrophic failure happens.
You know, it's pretty amazing when you stop to think about it. This simple device, an invention born from 19th century physics, remains the absolute bedrock of our entire electrical world. It's efficient, reliable, and it's what makes our modern lives possible. But as we move towards smart grids, renewable energy, and new power demands, it leaves us with a really big question. How will this unsung hero have to evolve to power the next century?